Okay, so for this video, we're going to cover the ideal gas law. Which looks like this: PV equals nRT. So I will explain what each of those variables mean in a second, but let's have a little bit of discussion about what an ideal gas is. One of the things that we assume, and this is a huge assumption that we make when we talk about the gas unit that you guys have been doing, is we assume a couple things about gases. We assume that they are really small, so they have no volume or weight. We also assume that they have no attraction to each other when they hit each other. So I'll write a couple of those assumptions down. So these are things that we assume are true. And because we assume these things are true, it allows us to use the different gas laws that you guys have learned. So the first thing we assume is that gases are small. Or gases, I'll say, have no volume. Now, we do have V's, like we have in this equation. What that volume represents is the volume of the container. But the individual gas itself, we assume it has no volume. We assume it takes the space or takes the volume of the container that it's in. So as long as we know the volume of the container, we don't have to worry about figuring out the volume of the gases. So that's one assumption that we use. The other thing that we assume is that gases have no attraction. Gas particles have no attraction. And what that means is when they collide with each other and with the walls of the container that they're in, we assume that they collide and bounce right back off. They're not attracted to staying together. Okay? Now, these are some things that we have to assume are true. Otherwise, it kind of messes with our pressures and volume things that we do in our equations. So an ideal gas is a gas that has no volume and has no attractions with other things. Now, one question they may ask on a test or quiz is, in what conditions will an ideal gas deviate or not behave like an ideal gas? Well, there are two conditions that could change our assumptions if we are dealing with high pressures. So I'll write it this way. So high pressures, so if we put a gas under extreme pressures, it's going to change how it behaves. And if we have very low temperatures, it also changes how a gas behaves. Okay? So if you think about this as an example, if we have something and we squeeze it into a much smaller space, so we increase the pressure, we are actually forcing those particles so close together, they may actually start to attract to one another, which is not a good thing for this assumption that we make. Same is true for low temperatures. If we decrease the temperature so low for a gas, we may actually be able to get them to stick with the things next to them and slow down, that we could get it to become a liquid. So high pressures and low temperatures would allow or would turn a gas into a different state. So it may turn a gas into a liquid, because if we're forcing them together, so if we're forcing the particles closer together, and if we're lowering the temperature and we're not allowing the gas to move as quickly as it's used to moving, we can actually cause this to not behave like a gas. So these are conditions that alter gases. So high pressures and low temperatures would alter a gas and have it behave not like a gas, not like the way that we would assume. So if we actually go through each of these variables for PV equals nRT, this is the ideal gas law. So we are assuming that a gas is behaving this way. And we also are assuming that we don't have very, very high pressures and we don't have very, very low temperatures, so that we can use this equation. Otherwise, if we do have very, very high pressures and very, very low temperatures, then we technically aren't allowed to use this equation. But we always assume that it's okay for us to use the equation. So if we talk about what these variables mean, T is temperature. Okay? It has to be in Kelvin. So if, for this equation, if you're given a word problem where the temperature is in Celsius, you have to add, so remember Celsius, we add 273 to get to Kelvin. So we have to have it in Kelvin before we can put it into the equation. Let me erase this part over here to give us a little more room to work with. So the P is for pressure. Now, before, when we were doing all the other gas laws, you had a little bit of flexibility. You could use whatever you wanted to for the pressure unit. Now we don't have that same flexibility that we did before. The pressure has to be in atmospheres or kPa. So those are the only two options. Millimeters of mercury, not going to work for us for this equation. Only atmospheres or kPa for our pressure. Volume, like always, has to be in liters. So the V is our volume, and this is the volume of the container, has to be in liters. Now this N, this is a new thing that we haven't talked about for any of the other equations that you guys have done. This actually is moles. And this is the same moles that you guys did in stoichiometry. So this is the only equation that we can use if we're given a gram amount or a mole amount. So they may say, you have 10 grams of a gas, or you have 25 moles of a gas. This is the only equation that will allow us to put in the amount of a gas, like moles or grams. Okay. And this R, this is called the gas constant. The good thing about this variable, it will always be the same number every single time. Now the number that you use for R is based off of what you use for your pressure. So there's two different R values that we could use. And I'll write them here. So R can be 0.00821 if you are using atmospheres for your pressure. Okay? So one thing with the R, the number that you use has to match with the pressure that you're using. So if your pressure is in atmospheres, you have to use this number for your R. If your pressure is in kilopascals, you can use 8.314, but only if your pressure is in kPa. Okay? So that's kind of defining all of these variables in this equation. So I'll give you one example of how we would use this equation. So let's say we have 33 grams of hydrogen gas is placed in a 8.2 liter container. At standard temperature. And the question could be, what is the pressure in the container? Okay, so a couple things. Let's identify the things that we were given. Let's first actually start with standard temperature. You may be given something called STP. So STP. If you're ever given STP, STP is a shortcut way of giving us two things. It gives us a temperature and it gives us a pressure. STP means that we're dealing with 0 degrees Celsius or 273 Kelvin, because we know we can convert that into Kelvin, and we're dealing with 1 atmosphere for the pressure. So that's what STP stands for. So when we say standard temperature in this word problem, that's a fancy way of telling us our temperature is 0 degrees Celsius. So we have a temperature. This is a gram amount, but remember, in our equation it has to be in moles, but we can do a little quick conversion to go from grams to moles in a second. So this would be like our N number here. We have this is our volume. We have our temperature. We said a standard temperature is 0 degrees, but the pressure we don't know. So we don't know the P value. So let's actually plug this in. Let's first start with converting into moles. The first thing that we'll do is we'll convert that gram amount into moles. So let's first start with, and now this converting into moles is going to be a little bit of a review of stoichiometry. It's not going to be as complicated as the stoichiometry stuff you guys may have done first semester, but it is going to be a little bit of stoichiometry. So you will have to be comfortable with converting from grams into moles. Because for most of these problems that you'll get for the ideal gas law, they're not going to give you the amount in moles. You're going to have to find the moles first. So if we're given 33 grams, remember hydrogen is a diatomic, it's H2. It has to travel with the partner. We want to convert this into moles. So grams are going to go on the bottom. And the reason why grams go on the bottom is because we want that unit to cancel. So if this was in the top, we have to put grams in the bottom so it cancels out. Now, we always have a 1 mole here. Now the number that goes here is based off of the weight of hydrogen. Hydrogen weighs about 1 gram based off the periodic table, but there are 2 hydrogens, so we're going to put 2 here. So if we were to do this division, we would get 33 divided by 2, which is 16.5. And this would be moles of H2. Okay? This is the amount that we're actually going to put in for the N value up here. So let's start plugging in some of the things that we know. Pressure, we don't know, so I'm going to keep it as a P. Volume, what they gave us, is 8.2 liters. Good thing is it's already in liters, we don't have to convert. So 8.2 liters. The N is moles, so 6.5. Now, the R, it's up to you. We don't have the pressure unit, so we have a little bit of flexibility. We could use either the 0.0821 or we could use 8.314. They didn't really say what pressure needed to be, but let's say in the word problem, let's say the pressure had to be in atmospheres. Okay? So that kind of limits us. Because our pressure needs to be in atmospheres, we have to use this one because that one is the one that goes for atmospheres. So for R, we'll put in 0.0821. Okay? Now temperature. They gave us 0 degrees Celsius. Well, they gave us standard temperature. We know standard temperature is technically 0 degrees Celsius, but temperature has to be in Kelvin. So we would add 273. So 0 plus 273 is still 273. So this is what it would look like with all of our numbers plugged in. Now to actually solve, let me erase this mole calculation that we did. Now to technically solve, the beauty of this is it's always a one-step problem to solve. If P is over here, we just need to divide by 8.2. So those cancel. So P would be equal to all of this, so 16.5 times 0.0821 times 273, all divided by 8.2. And whatever number you get for that, that would be your pressure in atmospheres. So this is an example of how we would use that ideal gas. This is one of the longer examples because we had to convert the grams into moles. But if this were a mole number, you could put it right in for N without any issues. Just 2 more equations that we'll do. Let me shift over here. We will do Dalton's law of partial pressures, and his equation is super simple and actually makes a lot of straightforward sense. So Dalton's law of partial pressures. So his equation will say something like, or is the total pressure. Now his equation deals with mixtures of gases. So we will be like, they may say something like you're adding nitrogen and oxygen and hydrogen together in a container. So his law deals with mixtures or mixtures of gases. Whereas all the other equations we've been doing so far are dealing with just one gas at a time, not a mixture. So his is a little bit different. His deals with a mixture. So he says that as long as you know either the total pressure of the gas, you can just add up all the pressures of the individual gases. Which kind of makes sense. If we have, a couple marbles in a bag, if we add up the red marbles, the green marbles, the blue marbles, we would know how many total marbles are in the bag. So he says as long as you know each of the individual pressures of the gases that you add, you can find the total pressure of all the gases. So an example of how this would work is it could be something like, let's say hydrogen, and I'll put it in actually chemical formula, make it a little bit easier. So H2, N2, and O2 are mixed together. Okay. And let's say the total pressure is, let's say, 38 ATM. And this doesn't have to be in atmospheres. They could give you the pressure in millimeters of mercury or in kPa. It actually doesn't matter for this equation. So let's say the total pressure of all the gases together is 38, and let's say H2 and N2 had an individual pressure of, let's say, 14 ATM and 23 ATM respectively. So they're kind of giving us each of them. And the question might be, what is the pressure of oxygen? Okay, so just to recap, we have hydrogen, nitrogen, and oxygen. So we have 3 gases mixed together. The total pressure of all the gases is 38. Hydrogen and nitrogen each have a pressure of 14 and 23. So hydrogen's contributing 14, nitrogen's contributing 23. And the question is, what is the pressure of the oxygen? Well, this is very straightforward. So let's say the first gas is hydrogen, and it doesn't matter how we label these. Let's say this is nitrogen, and this is oxygen. Well, we know the total was 38. And the total comes from adding each of those together. Well, hydrogen we know is 14, so I'm going to erase that and put a 14 atmospheres. Nitrogen we know is 23, but we don't know how much the oxygen is. So it's as simple as adding those two up. That would give us 37 total. Well, the total is 38. So oxygen has to be 1 atmosphere. So there's only a couple variations of how they could give you word problems for this equation. They could either give you each of the individual gases, and in that case you add them all up to find the total, or they could give you the total and some of the individual gases and have you find the missing one. In that case, it's a simple addition and then subtracting from the total. Very simple, straightforward equation. But again, we only use this for a mixture. So you would see, as soon as you start talking about mixtures of gases together, this is the only equation that we can use. When you start getting word problems that deal with moles or grams of a gas, or they ask for the amount, this is the only equation that we can use. Okay. And the last thing that we'll talk about, you guys may not actually do the rate of effusion equation, but we'll talk about what effusion means. And I'll give you an example of how that equation is used. There's an equation that's given to you in your book. Well, I'll explain how it's used just in case you end up getting it on a quiz or test. Alright, so let's stick it over here. So effusion, also you may have heard the word diffusion. It's just explaining how gases can move. So if you imagine like spraying a slight spray of perfume in the corner of a room, eventually that smell will go through the whole room as those gas particles move. So gas particles can diffuse or spread out in a room, or they can effuse. Effuse just means escaping from a container. So diffuse, gases can diffuse, that means gases can spread out. Or gases can effuse with an E. That means they can escape a container. So imagine like a balloon that has a slight hole in it. The gas particles that leave the balloon, we would say they're effusing out of the balloon. Whereas if we spray a perfume, or if there's a bad smell, we could say that that smell is diffusing or spreading out through the whole room. Okay, so Graham's law. And this is probably an equation that you will not need to know, but you will need to know kind of the concept behind it. But Graham's law deals with how things effuse or escape. The concept behind it is the higher the molar mass, or the higher the weight of the gas, so higher molar mass equals slower effusion. Okay? So if you think about it, something that has a bigger weight can't move as quickly. So a gas, if we were to compare two gases, let's say we were to compare hydrogen and oxygen. Now the weight of them, hydrogen weighs 1 gram for 1 hydrogen, but 2 grams will weigh about, or 2 hydrogens will weigh about 2 grams. The oxygen weighs about 16 grams per oxygen, but there's 2 oxygens, so oxygen weighs about 32 grams. So between these two, oxygen is a bigger sized particle. Oxygen gas would not move as quickly as hydrogen gas because it's smaller. So if they were in a balloon together and there was a hole in the balloon, the hydrogen would be able to move through that hole a lot quicker. That's all this means. Higher the molar mass of the gas, the lower it can escape, or the lower the rate that it can move. There's an equation that actually goes with this where you could calculate exactly how much slower or faster something moves. And it's set up like this. So the rate of gas A divided by the rate of gas B, so we're just figuring out the rate at which gases move, is equal to the square root. Now it switches. Even though this is gas A, we're going to put the molar mass of A on the bottom in the actual square root, and we're going to put the molar mass of B on the top, so it switches. A actually goes in the bottom in the square root, but B actually goes on the top, so just be careful with that. So if we keep on using our hydrogen-oxygen example, so we already have the weights, so the way that we would actually input this into our equation would be, so we would say the rate of, let's say hydrogen is A, to the rate of oxygen. So this is like a ratio or a comparison. So the rate of hydrogen to the rate of oxygen. Okay, would be equal to the square root of, so we want the weight of hydrogen, we said was 2 grams. We're going to put that here on the bottom. Remember, A, the gas that you designate as A has to have the molar mass on the bottom in the equation. So then molar mass of oxygen is 32, so we're going to put that up here. Well, 32 divided by 2 is 16. The square root of 16 is just 4. So we'll actually interpret what that number means. So we ended up with a 4. What that means is that, give me a second to erase this because I want to write out so you have that for your notes of exactly what that number means. So what the 4 means is that hydrogen, so it's always the first gas, so hydrogen effuses at a rate 4 times faster than oxygen. Okay? So if you notice, the 4 that was here is the same 4 I used here. So once you find that number, whether it's a decimal or a fraction or a whole number, it will not be negative, but you'll be able to compare. So we can say that the one on the top, so hydrogen, effuses or moves at a rate 4 times, because that's what the number that we got, moves at a rate 4 times faster than oxygen. Now let's say we had gotten a decimal. Let's say we got 0.2 or 0.4. Then we would just say hydrogen effuses at a rate 0.4 times faster than oxygen. Well, if it's a decimal, that means it's not really moving much faster. But that's how this equation works. Whatever gas you put on the top, that one is going to tell you how much faster it moves in comparison to the other when you solve for that number. But for a test or quiz purposes, the most important thing to know would be this concept here. As the molar mass of a gas increases, the rate that it can move or effuses decreases. So if you're given 2 different gases, you want to look at the molar mass. Whoever is bigger is going to be the one that moves slower. And that's probably the extent of what you will need to know for a test.